Introduce our silo speaker today. Will be Thiago Serra, who is from the Tippie College of Business at the University of Iowa. He got his PhD from Carnegie Mellon University and spent a few years also as assistant professor at Bucknell before joining Iowa. Thiago is very active in our optimization community. Last year, he was the chair of the Informed Computing Society. And we all look forward to his live social media posts about talks and stuff and keeps us informed of what's going on at any talks he's at. He works at the intersection of integration of machine learning and optimization, so he's a perfect person for giving a talk in this seminar series. So take it away, Thiago.
Thank you for the invitation. Very nice introduction. Thank you, everybody, for coming. Even if it's just for the pizza, at least doesn't look the room is empty for the actual talk, right? So what I'm going to talk about today is the general theme of what I've been doing as research for the last years, which is you have a mathematical optimization problem, and you could potentially put a neural network inside that problem as a modeling device. And if you do that, how do you go? So first, why would you do that? And then, if you do that, there are caveats. How can you handle those caveats when they happen? Is it good? Okay. And specifically today, I'm going to talk about the latest work we have, so which is using gradient-based algorithms for that. So this and the previous paper were co-authored between me and Jai-Tai Tong. Jai-Tai was an undergraduate student at Bucknell. He's now doing his master's at Northwestern, applied for PhD in a few different places, and we have a lot of fun with this. And for this particular work, we're joined by Meeting Zhu and his advisor, Sambira, and he brought some new things we were not aware of that really made our results much better. So it's really about fishing a little better because of that. Now, I hope you like Forrest Gump. Otherwise, it's going to be a whole hour of Forrest Gump. Okay, Forrest Gump, little Forrest here. It's going to be our hero. He's going through his way of learning about optimization and maybe neural networks on the side. So the lady on the bus asks if he's coming to optimization school. He said, my mom said to never optimize with strangers. And she says, right now, neural networks are the strangest thing around here. And he thinks that's going to be okay. So we have some pictures of his experience early in grad school. First summer, he went to a workshop. And if you know Jeff Linderoff over there, he has a reputation in computational optimization in North America. Whenever there is a conference, he makes people do human pyramids. And he has a catalog of all the names that he was already mentioned put in a pyramid or not. And as you can see, Forrest is here between me and Jeff in this picture. All other people were reading in that human pyramid. But I mean, this beginning of the PhD, he was very excited that everything is going to work well. 3 months later, by the end of that first summer, here he is. Things were not working that great. Not only, okay, he still had to find an angle to make these things work, but also he didn't feel worthy as an individual because he was still doing 3-2-1 pyramids, not 4-3-2-1 pyramids, right? Even though Bill Cook's on top, which is a great honor, but still 3-2-1 pyramids, results were not that great. So what is it I'm talking about here? I call it optimization over trained neural networks because that qualifies it properly and separates it from, for example, training neural networks. But the fancy trendy name that people have been using is, let's just take this out of the way, constraint learning. It's not a very accurate name, but it's catchy. So let's use the catchy name, right? So let's say you have an optimization problem. You have decision variables x and y. You're minimizing a linear objective function just to make life easier for now. You have some linear constraints, and you might be wondering, why are you seeing double? Because you have x and y, but everything is linear. Why don't you just bundle them together as a single vector of decision variables? I like framing it in this way, because then it's easy to do the next step. Now I have a neural network with the rest of the stuff. Some of my decision variables in x are going to be the inputs of this neural network. Some decision variables in y are going to be the outputs of this neural network. And I can change x, I can change y. However, there's a constraint. Whatever goes into the neural network as x has to result in y coming out of the neural network. So that's how we're using a neural network as a modeling device. Basically, a neural network can be part of a broader optimization model. Is that the only way you can do this? Absolutely not. You can reverse this if you want and have a neural network with a layer solving an optimization problem. And there's a lot of people doing that. They're very smart. It's just not what I do. I like doing it this way. Let's say, like in the long run, some problems are going to be better solved one way, some problems the other way. My brain works better with this. That's why I'm selling this to you, to be very honest. But this is a little abstract yet. So we're going to go through an example to illustrate where we would use something like this. And forgive me, it's a business school example, of course. It's a marketing example. Let's say we have 3 marketing campaigns we're working. We're in a company, we need to spend our money with advertisement because we want to sell more. Let's say that X1 is the number of ads that we place on Google. Every time we place an ad on Google, we have a cost C1. I'm ignoring these varies, just bear with me. It's just like a simple example to think through this. Let's say X2 is how much advertise on Instagram, X3, how much advertise on TikTok. And let's say I have a marketing budget because resources are always limited. That's the whole point of constrained seed optimization. So let's say if I calculate how much I'm spending, that should not exceed my budget. And of course, we're advertising because we want to sell. So I want to sell, let's say, the basic version of my product. Let's say that's product 1. And Y1 is going to be the number of items that I'm selling of that first product. Each one has a price P1. Let's say Y2 is the fancy version. And well, I can have a decision variable for how many units I'm selling. And each one sells at a price P2. Which means if we want to maximize profit, roughly as revenue here minus the marketing cost, I don't know the other costs, should put them here. This becomes maximizing how much money I'm making from the sales minus how much money I'm spending advertising. So if we put all of this together, we have this maximization of a profit here. We have a budget on the constraint, on a constraint on the budget. And we know we're not going to be doing a negative amount of advertisement. We're not going to be selling a negative amount of products. But something is missing here. If I solve an optimization problem like that, what's the optimal solution?
Infinite.
Cell infinity, right? There's no constraint on the y's. What about the x's?
That's 0.
Why were you going to spend money? Then you get nothing from spending money, right? So there's no connection between x and y. And that's basically one thing we can do from your network. Let's say if you have enough data, you could learn from your data what happens in terms of sales of different products, depending on how you're advertising in a particular day, week, month, and so on. Assuming that you have that data, right? And the point here is we're not expecting that to be a linear function anymore. Because, well, if you have placed 1,000 ads on Google, you know that the next one is going to have a much smaller impact than when we went from 0 to 1, right? So there's a diminishing return there. Not only that, but if you are advertising very heavily on Google, putting one ad on Facebook is also going to have a smaller impact than if you were advertising less on Google. So you know that in many ways, there's going to be some interdependencies here. Even if this is a function that's monotonically non-decreasing, probably increasing, it's still going to be a little tricky to model this in a linear way. So we're just going to assume that the neural network is still going to do that for us. Which brings us to two possibilities for using constraint learning. At least that's what you're going to see in every talk that talks about this. First, we do not know the mathematical formula connecting ins and outs, but we have data. So use the data, and we don't have to think about it. Well, maybe the data is predicting how much you sell. Great, you don't have to think about it. Or even if you can write the formula, it might not be a good idea. Think about power systems, chemical processes. There's a lot of nonlinearity. And if you start multiplying decision variables, it doesn't get that nice to solve anymore. So typically, we prefer to have a linear model, even if it's a little bigger, because we know better how to solve that kind of problem. For now, imagine many of you here in this room are trying to change that, but we know that linear tends to be easier to solve. And even in machine learning, something closer to linear is going to be a little better. It's going to be a little safer sometimes. And of course, people have done a lot of that. There's some frameworks that you can use. Bob is going to guide us from some literature review here. There are frameworks like ReLUs, Omelette, OCL, OptiCL, and more recently, Ruby has their own library for integrating classification trees, neural networks into a mixed integer optimization formulation. There's some variants for stochastic, robust, bi-level optimization, which I didn't mention here. This has some applications inside machine learning. Essentially, when you start solving optimization problems over the neural network, that's how you do network verifications, special case. You can measure model complexity. You can use that for pruning. You can use that for generating counterfactual explanations. And also, if you learn a policy, you can also limit your decisions to what is feasible or not. So in the context of reinforcement learning. And outside machine learning, there are also some other applications, some interesting ones, for example, power generation, like industrial automation, molecular design, chemotherapy, that they're all places where you may have a lot of data or you have functions that are highly nonlinear, and you can just put a neural network to represent that part for you. So going back here, but why a neural network? Well, like many things, because we can. If you think about a ReLU activation function, a ReLU activation function is piecewise linear. So if you think about every neuron, we can model whether that particular neuron is active or not. And that's going to create a mapping between the inputs and the outputs, which means that if you have a neural network where all three activations are piecewise linear, among which ReLU is one example, it means that you can write this optimization model without any nonlinearity. Of course, there's some binary variables there. That's not free. That's going to really come haunting us back later, but that's part of it. Now, just to go for a few details to make sure we're all on the same page. So I'm assuming we have a feed-forward neural network from X to Y, and that within a unit, we have basically a combination like the inputs of that neuron are multiplied by weights plus a bias. If the output here is negative, what comes out between the maximum between this output and zero is going to be zero, which means the neuron is inactive. But if you get something positive, you say that neuron is active. So this is what we call the reactivation output. Sometimes we write that as G, if you see that in the notation. And what we have over there is the actual output of the neural network. Now, I do have another example because there's some very interesting things that happen in a neural network, especially a ReLU one. Each neuron here is doing two things for us, right? First, it calculates the value of a linear function, like a linear regression. And it's basically a linear regression, right? Every neuron is doing a linear regression. So we're calculating some value like that. And then we take the maximum between that value and zero in the case of ReLU. Now, what can happen? We can get a positive value and send that value forward. Or we get a negative value and we send a zero forward. And for me, honestly, I find it very puzzling that someone would choose to send zero rather than the value that's here, because it feels like we're missing some information by just censoring that information, because it could vary a little bit from one input to the next. And having spent 5 years in a liberal arts college, for this question right now is that the silence speaks. Sending that zero has a powerful it's a powerful way of expressing a more complex function. And we're going to get down that route in a little while. All right, but ReLUs. We're not in the 2010s anymore. Actually, my son just reminded me we're in the late 2020s, and that really scared me. But, well, ReLUs are easier to train. You can approximate other trendier activation functions with ReLUs, like a GALU. Okay, a GALU is differentiation. You got my point. Differentiable everywhere. ReLU is not at zero, but well, there are many things that like in some ways we can make one approximate the other one. It's easier to embed a ReLU in optimization because except for this kink that we can try to model with a binary variable, everything else is linear, which is different from other activation functions. And we can make a lot of sense of ReLU networks, and that can help us solve an optimization problem based on a neural network trained with ReLUs. So we're going to talk a little bit about the fact that it's easy to embed them first, and then about making sense of them. One more time, just make sure nobody's lost behind. We're talking about optimization over trained neural networks, not about optimization to train neural networks. Just make sure. Sometimes that comes later. All right, so I mentioned we're going to be modeling here a neural network with linear constraints. And the way that this happens, the way that we do that is that we're going to have a binary variable modeling whether the neuron is active or not active. We're going to have what we call big M constraints, basically turning on and off the mapping between the pre-activation output and the output. And this is more or less how this looks for each one of the neurons of the neural network. And these big M constraints here, they're the source of nightmare. And the way that I teach my students in Iowa that you should never use a big M unless you really need to is reminding them of Michigan. And I think in medicine that works too. So, and the thing is, if you have a neural network with a lot of big M constraints, you need not only a good formulation, you need only not the formulation, but also hope. Because very quickly, it's going to get very hard to solve these problems because of an optimization problem full of binary variables where you have a lot of these constraints here. It's not going to have a very strong relaxation, meaning that the moment you relax, these binary variables should be either something between 0 and 1. Anything is possible. So there's a lot of nuance because of that. There are good and bad and ugly things about combining these two things. Good things. Neural networks can approximate almost anything. So if you have a Borel measurable function, you can approximate that to an arbitrary level of precision, as long as you have a sufficiently wide or deep neural network. You can do some combinations of that. There's plenty of theoretical results on that. On the optimization side, MIP solvers can find global optimum. Once you have modeled as a MIP, you can find the best solution. And that's a tricky thing. I have reviewed a lot of machine learning papers and machine learning conferences from optimizers where they forget to mention that. And then it's me debating with the other reviewers that, no, this is a global optimum. That's why they didn't run for all the time. That's why they're not reporting the runtime, for example, or they're just reporting the runtime and not a gap. There are ugly things, there are bad things. We cannot use very large neural networks for that purpose yet, but we're working on that. And the optimization solver struggles very easily because of those big M constraints. And then there's the ugly part. You come with a paper like that, everybody tells you don't belong where you're trying to submit. Machine learning doesn't think it belongs there, person research may think it doesn't belong there, so you have to really massage both sides to make sure that they're sufficiently happy with the contribution so far. Now we're going to get to the second part, and it's going to get more interesting. We can make sense of ReLU networks. There's a wider body of theoretical knowledge about what do you get with a ReLU network, because they have been used for a long time, and we can use that in our favor when we're trying to solve an optimization problem involving this kind of neural network. So what's the right way to do constraint learning? Every optimization problem, not only these problems, any other problem that we try to solve in practice, is going to have a specific structure. The best that we can do is know what are these special structures so that we can exploit it when we're designing an algorithm. So now we're going to go on a geometry trip, which I think is quite interesting. So if you lost your interest because optimization is not that fun, you can watch the next third of this talk without caring about optimization at all, which is going to be to your benefit. So here's Forrest. He's very advanced in his PhD, and he's an optimizer, and then he goes to like a seminar like this and meets someone that is more into neural networks. And then he comes with his bullshit about neural networks. Neural networks are like a box of chocolates. You never know what you're going to get. She knows better. And she says, not quite. And then you're not seeing, but there was a whiteboard behind, somewhere behind those trees, and they went to the whiteboard, and there was a long debate after. And we're going to see the summary of that debate. So basically, when you have a ReLU, you have a piecewise linear function, right? Every neuron is a piecewise linear function. You have a linear transformation, after which either you have a zero function or you have an additive function. And if you compose ReLU after ReLU in parallel, in sequence, any way you want, you're building more complex piecewise linear functions. And it's not going to be a linear growth. It can grow exponentially in the depth. It can also, as the neural network gets wider, this can grow polynomially. So the number of pieces of this piecewise linear function is quickly going to grow. And that can allow you to express very complex functions as a consequence. And how are we going to characterize that? With something that we call activation patterns. So let's say you have an input X. When you send an input X through a neural network with ReLUs, that's going to turn some neurons on, some neurons off. And now the signature of the neurons that it's turning on is going to define for us a linear region. when you're saying that certain neurons are on and some neurons are off, you're basically picking what the neural network does, which is a composition of linear transformation and masking, linear transformation and a masking, linear transformation and masking, and you're saying that all the masking is fixed. So the entire thing is going to collapse. And for each signature, the behavior of the neural network is going to be the same linear behavior. So the moment you fix the signature, the neural network is going to be a simple linear regression. Each signature is going to have a different one. So we can say that the linear region is richly defined by all the points that define the same activation pattern. So different regions of the input are going to be activating exactly the same neurons, and because of that, any differences of output between them are going to be linearly proportional. They're going to be they're going to vary in an affine way. Sorry, like words are missing today. So thinking that this is about turning things on and off, you can guess, well, maybe if I know how many neurons I have, 2 elevated to that number is the potential number of pieces in this piecewise linear function, which looks like quite a large number and looks very promising. But in practice, we don't get that far. I mean, there are lots of things that are going to prevent us from having a neural network where every possible activation pattern is going to be feasible, right? Some activation patterns are not going to match any possible input because there are going to be some conflicts between them. And to get there, I'm going to show you 2 geometric elements that are going to help us understand this. The first one is the concept of an activation hyperplane. Let's say get a pre-activation output I mentioned before, that linear transformation, that linear regression inside the neuron, and you equate that to 0. This is going to define a hyperplane for us. On one side of this hyperplane, you have the points that are activated by the neuron, that are the points that activate the neuron. On the other side, you have the points that are not, that do not activate the neuron. So basically, you're breaking the input into 2 half spaces for each neuron that you have. Now, if you think about a layer, you're going to have hyperplane arrangement where you have all these hyperplanes going different directions and breaking the input space into different chunks, and these are going to be polyhedral. And the maximum number of regions, full dimensional regions that you can find, are going to depend on 2 factors. One is the number of hyperplanes or neurons, and the second one is the dimension of the space, and this is trivial. I mean, we can assume, let's say, if a layer receives inputs of dimension 10, the 10 is the dimension of the space. For now, that works. Later, we're going to see that this actually gets a little, that can actually be smaller than that. But with these 2 pieces, I can start showing you examples where you cannot have every possible activation pattern being feasible. And I mean, why would we care about that? Because negative results are important. We can find the limits of what we can approximate in practice, and we can also compare different configurations. So let's say we're training, I know it's a very beaten example, but you're training some neural networks on the MNIST data set, because that's where you always start, right? It's like the MIP-lib for optimizers. Let's say you have a neural network with 18 neurons, 4 neurons here, and then 10 outputs. Let's say you have another neural network with 4 neurons here, 18 neurons here, and 10 in the output. So the basic difference is the flipping the width of the first 2 layers, of the hidden layers. And to wonder like how much that affect the results. It turns out that one of these architectures is going to have, in practice, a much larger number of linear regions than the other one can ever get, according to theory, which is one interesting piece to talk about. Okay, but trying to understand this geometry. Let's say I have let me just pause here because I think I'm speeding up. We're limited 3-dimensional human beings. The only way we can walk through something interesting is if I stick my examples to 2 dimensions. It's just life, right? So I have a neural network that has only 1 layer and only 2 inputs. I cannot put more inputs because we cannot see them. And I'm going to put 4 neurons. And then you can wonder, well, potentially we could have 16 different pieces in the piecewise linear function when we train this neural network. But we're never going to get 16. Because this is essentially the same. So like this is how much we can get. We can get as far as 11. And the reason is what we're doing here geometrically is if the inputs are 2-dimensional, these activation hyperplanes are going to be lines. And this is the same as asking, if I have a piece of paper and I can draw 4 lines, how many full dimensional regions can I get? You can never get past 11. So spring break, you're going back home, you're seeing some annoying cousin, little kid, they want to get them entertained for some time, offer them some real money if they can draw 4 lines and define 12 regions. They're going to learn some geometry and you're not going to spend any money with that. But and how does this work? You have this summation here on the number of hyperplanes, and at the bottom here, we go as far as the dimension of the space. So if we're in 2 dimensions, we have 4 choose 0, 4 choose 1, 4 choose 2. If there was a 3rd dimension, so we're talking about 4 planes in a 3-dimension space, we would add a 4 choose 3. That would be 15. But it's only with 4 dimensions, that, let's say 4 dimensions for 4 neurons, that we would potentially get 16. We may not get 16, but we can potentially get, depending on how you train the neural network, depending on the weights that you get. Now, this gets even more interesting when we look into deep neural networks. So this example here, credits to my co-author, Christian. It's beautiful. Again, everything is dimension 2 because otherwise we cannot see them. Let's say you have 2 inputs, x1 and x2. First layer, we have neurons A and B. They read x1, x2, do some linear regression here, do their activations, send something to C and D. C and D receive those inputs from A and B, do something, send them to E and F. So let's first break this like layer by layer. So A and B, they receive x1 and x2. We directly calculate the output of A and B based on x1 and x2. And we chose this example so that you can see the activation hyperplanes, their lines, and you can see that we have every possible combination. A and B are active, A is active, B is active, nobody is active. Then when we're talking about the second layer, C and D, they're seeing what comes out of A and B. They're indirectly seeing the inputs. They're not touching the inputs directly, right? And you can see that we're defining also 4 regions. And then E and F are also defining 4 regions. But now that's where things start getting interesting. That's where we started playing with this. If we think of what this is producing a function for us, that function is going to have the dimension of the output is 2 across every layer, but the dimension of the image is not. So if both A and B are active, it means that the output is going to vary on both dimensions. So we can say that the image of the function on this part of the domain is 2-dimensional. But if you look here in this gray area here, where A is active and B is not, the output of the first layer is going to be a positive value for A and 0 for B. Conversely, the other side, we're going to have the same thing. One value varies, the other value is fixed. And at the bottom, A and B are 0, which means we cannot distinguish between any of the points at the bottom here. And this is where things get more interesting, because what C and D are going to see is what comes out of that. So for each one of these regions that we define for the first layer, this arrangement is going to look a little different. So when we put C and D in terms of x1 and x2, it looks like this. So it's as if we were sending light through different media. You see these hyperplanes bending about. In the part of the space that there were 2 dimensions in the image of the function, we're definitely breaking this into more pieces. We're breaking again in 4 pieces. But in these areas here, where we only had 1 dimension effectively, we could only break it with 2 neurons. We could only break this into 3 parts because effectively the dimension there is 1. And at the bottom here, where like the 2 values are basically 0 all the time, we cannot break this anymore. And then you have to think about what is the smallest dimension across, like what is the smallest number of neurons that are active across all the previous layers to think about what's going to be the image, the dimension of the image of the function going forward. And the dimensions start going down and down and down. And this actually gives us like a much tighter bound to how far you can go in terms of linear regions, which is this theorem here. And I'm going to spend 0 time explaining this. You can forget that you saw this. Just imagine that, like, thinking about this and sweating for some time, we came up with a magical formula that I don't know if it's right or not. Nobody ever objected to it, and it was peer-reviewed. So maybe it's mostly right. But we can calculate some interesting things and interpret some interesting things out of it. So this is something that we did in that paper that I found very interesting. So let's say you have 60 neurons, a budget of 60 neurons, and you don't know how to distribute these neurons. Do you put them in more layers, in less layers? So, and we chose 60 because 60 divides by 1, 2, 3, 4, 5, 6. Makes life easier. So first thing I could do is I could put 60 neurons in one layer. How far can I go in terms of linear regions according to the upper bound? Well, depending on the size of the input, this is how far we can go. Now, let's say that instead of having one layer with 60 neurons, we had 2 layers with 30 neurons. Now, our result is a little tighter in that sense. So it's saying that we not go that far compared to like the results that existed before us because of this bottleneck in the dimensions. And this keeps happening as you increase the number of layers for the same number of neurons. So what's interesting here is that if the input dimension is very large, a shallower network would define more linear regions. But if you fix the input dimension, let's say you're aiming for like 12, maybe 3 layers is better than more or less layers. Now, this is very speculative, but we just started wondering, well, that this starts showing some hint of what we could do with this. Now, we did some experiments to see what happens in practice, MNIST, of course. And then what we tried was, let's say we have 22 hidden neurons, and we can distribute them between 2 layers. Between 1 and 21 in the first, the rest in the second, and then for output. And we got this plot here. So this dashed line here is 2 elevated to the number of neurons. It's like the first upper bound. And well, you can see like it doesn't distinguish between the different cases. So what we did here in the x-axis was we varied putting, like starting with very few neurons in the first layer and a lot in the second, and slowly putting more neurons in the first layer and fewer in the second. So this red line here is the upper bound that we got. And these blue dots here is what happens in practice. So there is a considerable gap, some spots here, which means that potentially we could tighten this bound yet. The other thing that there is one thing that we omitted from this plot when we submitted the paper, because we were concerned about the reviewers not understanding it. We had a lower bound on the maximum number, and that lower bound was right between these two, weirdly closer to the upper bound, which means you can potentially construct some neural networks with lots of pieces. In practice, when you train the neural network, that doesn't happen. But we thought if we had a lower upper bound, a lower bound, and the actual number below, we would get like slapped for that. But we didn't have the math to explain that. A year later, some folks had the right math, and they showed in practice that, yeah, we can construct potentially very complex neural networks. In practice, when you train, it's not going to be that expressive. And as I promised before, so if you have 4, 18, 10, this is the upper bound. If you have 18, 4, 10, this is the actual number. So it's some orders of magnitude above, which is something interesting that like the theory is telling us, maybe confirming what we see in practice. And in terms of accuracy, things are a little weird. So here we have the number of linear regions, and here we have the training and the test errors. So as you can see, it's a mixed bag. It's super weird. But the thing here is, this is a heat scale. Here we have very few neurons in the first layer. Here we have very few neurons in the second layer. If any of those layers is very narrow, you're messing up the information. I mean, the output layer cannot do anything with it. So if you just throw away the 2 extremes, let's say have at least 4 neurons per layer, actually there's a very interesting correlation here between the number of linear regions and the error that we get both for training and test. And what is very interesting here, we're talking about 32 neurons, and this is giving us a piecewise linear function that can have as many as 10 million different pieces. So that's where this expressive power comes in. And it comes in because we're zeroing out stuff instead of sending those negative numbers going forward. So essentially, when you're training a neural network, it's as if we were doing a piecewise linear regression. I mean, we cannot, depending on the architecture of the neural network, there are things we're going to be able to obtain, and there are functions that we wouldn't be able to obtain, of course. It's nuanced, and we don't have a full theory for what we can and cannot obtain. But intuitively, you may wonder, well, the more pieces, potentially, the better we fit the data, right? And what's interesting is these pieces, or linear regions, they're all polyhedra. And they're polytopes if you're bounding your inputs. Let's say if your inputs are always between 0 and 1, you're just talk about polytopes, geometrical objects that we manipulate in optimization and have fun with. Now, that polytope is defined by which neurons are active or not. The wider the input and the top layers, the more polytopes we have. So the size of the input matters a lot because that is going to reduce that effect that we have discussed. And this is going to matter a lot from the experiments. And the more polytopes, the more expressive the model is. So we're back to the conversation. They're back to sitting, and Forrest is still trying to offer the chocolate. And this is where it ended. Neural networks are more like a box of polytopes. Here's an optimizer. And when you say that word, things turn around. She said polytopes. Optimizing over each polytope is not that bad. When you have an optimization problem where the feasible set is a polytope, everything is linear. It's a linear programming problem. You can efficiently solve very large instances of linear programming problems, which means you can very conveniently handle that kind of nonlinearity now locally. So this brought us to this idea. That's where we have been working with Shaitai for some years now, of why don't we design a local search algorithm based on that? So what we do is, given a linear region, we find the best solution around us. Then we move to another linear region next to it, and we repeat. And at some point, we're going to get stuck somewhere. It's not going to be the global optimum because I'm not making any assumptions about this piecewise linear function, but if you just do that enough times, you're going to find some very good results. Visually, just think about it like this. Initial solution A, we move all the way to B. Then let's say from B, we do a slow step, and we're in a different region, where we can slowly move to another solution, jump again, do that again, jump again, do that again. And we're very excited about this idea. And then we found that some people started doing this before us, which was comforting, and it was scary and comforting at the same time. Scary because we thought, wow, they did it. And they even knew linear regions, they explained it all in all the concepts and cited this previous work. At the same time, we found some interesting ways to do it different than what they did. And they had a benchmark. We just had to work on the same benchmark to show how this would work. And have another example here. I'm not a big fan of writing papers, large language models or other things, but vibe coding plots, oh boy, I'm in love with it. I had this experience last semester, and it's just amazing. It's always cool in that level. So this is another example. Let's say I have a neural network, 2 inputs again, and now I have 5 neurons. For every neuron, I have some linear transformation, then the maximum between that and 0. And then I'm combining them in a final output. Some are negative, some are positive, just to make it interesting, right? So I can converge somewhere. So this is PyPlot. This is not a fancy library. This is PyPlot, but I have queried Copilot for long enough and in such an annoying way to get it done the way I wanted, that either I would have spent a week to do this, or if I had asked a student, I would lose this student. But it's beautiful. So what do you see here? There are 3 neurons, same colors here. You see the activation hyperplanes for each neuron. 1, 2, 3, 4, 5. If these little balls, I never saw that in PyPlot. PyPlot is beautiful if someone can do it for you, And then you have little arrows telling in which direction is that neuron active. But given the pluses and minuses here, I also have in which, once they're active, is this a positive or negative contribution? And given the magnitude of these coefficients here, is this a big contribution? Is this a small contribution? So it tells you a lot of stuff. It's beautiful, and I didn't have to do it by hand, so which is great. And then it's not very hard to, let's just put some dashes here, and now I can do some contour plots here, and you can see the piecewise linear function. And you can see, well, it doesn't matter where we start. We should be converged here. This joint here, this crossroads here of linear regions is where the local optimum is, at least between 0 and 1 for both dimensions, right? And I'm going to illustrate now how 3 different algorithms have been going about this. So this is what we call the mid walk. It's the work before us. That's not how they call themselves, but we wanted to have a simpler, more unifying terminology for this. The way it works is, from a starting point, let's say A, we find the best solution across all the linear regions around. So from A, well, we're in one linear region, we get to B. Now that we're in B, this point B is not in one region. This point B is in 4 regions. We look across 4 of them. What is the best thing we can do? Go to C. Done. 2 steps, we found the local optimum. So, and we repeat this from the new solution, as I mentioned. Now, some observations here. So, if the activation hyperplanes, if the activation hyperplanes that contain X, let's say when you're in B, we have to search on both sides, right? We cannot just look at one linear region, which means that if X is not an interior point, we're solving a MIP. It's a local MIP. We're not solving it considering all the activations that can change. We're just solving it flipping, like, let's say 2 and 4 in this case, or flipping 1 and 5 in this case. So it's a little smaller, but it's still a MIP with big M constraints, which means, and that was our happiness because, okay, someone did this before, but is there a way we can improve it? Well, they're still solving a MIP. If we just make the neural network have a sufficient number, like be big enough, this MIP is not going to solve. Even like this smaller MIP is not going to solve. So each step is cheaper. Okay, yeah, sorry. I thought I messed up. Each step here is going to be cheaper than solving the original problem that we would solve at once. But on larger networks, this is going to get very expensive. So this is what we did in our first paper. Okay, we start at A, and we find what's the best solution around. Well, the best solution is going to be this corner here, but I didn't stop here. Well, if this is the direction where things improve, what if I just nudge this a little bit more so that I fall in the next region? So that I don't have to make a decision about on which side I am of these hyperplanes. I just throw myself in the next one, hoping for the best. Is it going to be as good? No, but it's going to be good enough. So basically, like we got here and we jump a little further. From B, we do this again. We go in this direction, push a little further, we're in C. From C, we get to this point, and then we push a little further. From this point D, we go back to the same point as before. Okay, I guess we're stuck. I guess that's time for stopping. Observations here. We're always solving an LP, not an MILP. So now it solves a lot faster. You have a small improvement per step. As you can see, I'm even taking more steps to get to the same place. But each step is much cheaper than before. And it pays off when the search space is very large. And that reflects on having neural networks more and more linear regions. And what we did now, we went cheaper than that. We could potentially look for what's the best solution in this linear region. But why bother? This is a local decision, and it's not going to be where you're going to converge anyway. Just look at the gradient. In which direction do things get better? Move that way. And you don't need to find the best local solution. You need to go in the direction that's going to maximize the final result. So there's some optional switches here that we're going to discuss. One of them is make this step long enough that you get to the next linear region or not. The other one is eventually we're going to be starting like hopping on and off we were going to start bouncing around because of the structure. This is a piecewise linear function. It's not that great for like a gradient descent. Or maybe it is. I just need some advice from some people here. But so if we felt like, okay, we're not improving anymore, let's add a perturbation to make sure, to hope that we can converge better from this point on. And repeat from the new solution until we feel that we're done. Observation series. This is going to leave each linear region faster. So it may converge a different local optimum, but it's just going to be faster. Even small improvement per step, but each step is much cheaper than before. Linear programming is efficient to do, but it's not going to be linear. But like a gradient step, that's a linear thing. It's much better in that way. So this is going to pay off as the search space keeps growing. For smaller neural networks, you don't do this because this is not be a good idea. But for larger neural networks, absolutely. So here's some results from our first paper because I think they put a good context. So that first paper we compared with like what we call MILP walk. It's a paper by George Perakis and Astilios Tsurbas. But we increase the size of the neural networks. So what we're testing, input size 10, input size 100, input size 1000. Depth 1, depth 2, depth 3. Blue dots, the width is 100. Red dots, the width is 500. We're measuring for a given time limit. What's the largest value of a solution that we can get when we're maximizing a neural network that that has like a single output, basically representing like a function with like a single dimension for output. And their work is what we call MIP walk. It's interesting to observe that for a small input size, they beat us big time, especially as the neural network gets larger. And the reason for that is if the input size is smaller, because of the dimension, effectively, the number of feasible linear regions is very small, which means if you have an algorithm that is very expensive per step, but does a very good job, you're likely going to converge to a much better solution. But as you start increasing the input size, it flips things, right? So at this point here, with input size 100 and a width of 500, we were doing much better. And the input size of 1000, adding some depth, even for input for like a width of 100, we were doing better than before. So which means, okay, there's a balance here. And I think that's the honest way to represent an algorithm. Well, we design it for a certain purpose. There are places where it's going to win, and there are places where it's going to lose. And that's also how we evaluated replacing this algorithm with something new now. So what we're comparing now, we keep changing names. So we call it simplex walk. That's what we call the LP walk from the previous paper. It's going to be the red plots. Then we have projected gradient ascent, as we were maximizing, and Jaitai is very specific about ascent and descent. So these are playing algorithm. And it's projected because the input is really big, because the inputs are between 0 and 1, so we cannot like shoot outside. Then you have perturbed PGA, when we're in those perturbations, when we don't seem to be getting any better. And then we have PGA linear region, which is basically an extra step where if we realize that we can jump a little further because it's going to be keeping more of the same, we do that and accelerate the process. We may miss something in between, but it may help in some other ways. What we tried with neural networks, input size 10, 100, 1000. Layers, number of layers 2, 4, 6, and 8. We went crazy because we had to see when are we going to do well and where are we going to do worse. And with 100, 1000, and 10,000. So first profile here, just like this is combining all of these different configurations, just looking for runtimes. What we can see here from the curves is refining this gradient algorithm pays off. So you can see that in all of the cases, like the blue line is above, which means it's a little better than the yellow and the green. Now, I have never worked with this kind of performance profiles before. It's beautiful. It takes some time to absorbing this. So the way this works is, what we have here on this side of the plot is how often that particular algorithm found the best solution across all algorithms. When we get to this point, we're going to see, okay, how often does this particular algorithm find a solution within 1/10 of the best solution found across all algorithms? And here, like 100th and 1000th. So basically, if you just want to know who won most of the cases, you just look at this extreme. If you want to know how the tail looks like, how bad are the other cases, you look at how this plot looks like. So as you can see, as we refine the gradient algorithm, we got like better and better results comparatively. And those results didn't change much by time limit. But simplex walk, that one based on linear programming, if you give it enough time, it starts making its way up. You just have to give it a lot of time depending on what problem you're solving. So the refinement pays off here. LP walk becomes more competitive if you give enough time. Second plot, we're comparing input sizes. And now things are a little different. If the input sizes are 10, the gradient algorithms are almost all the same. Okay, like refinements matter. I mean, like going the perturbation helps, but the linear regions don't. And I mean, simplex walk is not that bad. As you start increasing the input size, things change. Having a more refined algorithm that does it the right way and exploit the structure and is faster is going to pay off. Okay, so that's basically what I just said. And we have more linear regions going to the right here, which is like how we orient ourselves. But looking in other ways, because we have to see where you lose and where you win, right? We have like we have an 8x8 matrix in the paper. I'm just putting the parts that are relevant. So smallest depth, smallest width. LP walk beats everybody because, well, locally, those are the best possible decisions. If you just have, and it's enough time for that size of neural network. So you can see for 3 of the plots, the algorithm we had before was better. But as we move down, and to the right, all the way to depth 8 and width 10,000. It flips everything. Now that fancier algorithm with all the bells and whistles beats everybody all the time. Which means that as it gets larger, you need to have a different type of algorithm, a little faster, maybe not the best local decision, but just fast enough that you can go for this search space you can explore more of the search space, right? You're not going to explore everything, but you just, when you think about heuristics in optimization, and the best source for that are like the papers from the 80s, the 70s, you don't have time. You're not going to find the optimal. You just have to be fast enough. There are lots of like wisdom that if you just look back and you look at a neural network, which is like a crazy problem for today's standards, you can apply those ideas here. So smaller networks, simplex walk does a great job. PPGA gets better, it's better than PPGA. You can see like even like the gradient away from here, like the linear region jump, it's not a good idea. But as you move this other side, everything flips. All right, now Forrest feels a lot more confident. He got better results. He even feels like he could be at the bottom of a 4-3-2-1 pyramid because his machine learning friend is on top and like supporting him. And yeah, there was a lot of distortion because this one Gemini had a hard time doing. You can see like shapes are a little different, but we got there. And Jeff Liederoff is there as well, as you can see. All right, wrapping this up. We presented a new local search algorithm for constraint learning. This algorithm exploits the structure of the neural network in the MLP model that we could have tried to solve it otherwise, finds better solutions when the number of feasible solutions is larger, and scales better because it takes less time per improvement step. And interesting fact, all of this, I mean, this slide has 2 years because when we presented the previous paper, it was exactly the same thing we did. And we basically exploited how to do something fast, exploiting structure, and we just extended that further. So where should we go from here? Well, I don't think, well, this is my son. Now he's almost 12. Not that cute, but you know, I love taking these pictures in PhD. And I love the cover of this book. It's the most intuitive cover because it tells you the difference between linear programming and integer programming. Well, your linear constraints are here. The moment you have the variable should be integer, actually what you need is something tighter. And this is the holy grail integer programming, right? This picture tells you what we're looking for and very quickly conveys the idea of integer programming and how that differs from linear programming. What is the theory that we need now? I don't know. I mean, trying to find that. And how does that going to look like for the next generation? Well, Forrest's son is going to go to a PhD someday. And he's going to say that his dad said not never to optimize with strangers. And the lady is going to say, now Gen AI is the strangest thing around here. And now it's up for little Forrest to figure out how to do with that. If you feel like doing it, and if you're not yet a PhD student, please don't. Only if you're not yet a PhD student, please. I don't want trouble. We do have a very nice PhD program, 3 hours drive from here, and you can come visit friends and collaborate with them here. Application deadline, January 15. GRE required, which is a pain and makes me lose a lot of students. Here's some like references, papers that have to do with what I talked here, theory of linear regions, papers about optimizing over neural networks. And there's a bigger picture in this survey here. You can find all of this on arXiv. This survey should be going any day online at IGNOC now. And that's it. Thank you very much.
Thiago, we have time for a few questions.
So in the new method, the local, I didn't quite understand, how did you choose the step size, or is it different for the different methods? What do you do, a gradient? What did you?
So we take the gradient from.
That just go to the end where you feel like an LP and.
Good point. I don't know what's the default choice for the step size.
Okay.
In the fancier algorithm, we take into account how long it takes to leave the linear region. So we can measure for how far we have to go if we want to change the gradient. So there's some customization there. I don't remember what's the default choice. There was a default choice. There was some validation on that. So we solved like a few optimization problems first. shows the hyperparameters of each one of the waveforms.
I think we'll wrap it up here.
Okay.
Looks like you're going right to get out in the snow. So thank you very much.
Okay.